Hi guys, here it's Fede, MATLAB Student Ambassador of the University of Pisa. In this short video we are going to discuss an easy and brief implementation in Simulink of a neuronal model. If you haven't used Simulink yet, please check in the description our two videos on Simulink. One is Introductory and one is a Strengthening. So, enjoy! So before starting, we are going to briefly discuss with a couple of slides the kind of model that we are going to implement in Simulink. Specifically, this is the same project that we implemented also in the final demo of the introductory video on Simulink. The model that we are going to consider is the Izikevich model, which is represented by two differential equations. One regards the action potential of the neuron and is a function of V, the action potential, and the other one is as a function of a recovery variable U. Also, additionally to these two differential equations, there's a reset condition which is responsible for the actual reset that we have in our neuron once we reach a spike of the action potential. In particular, when the action potential reaches a level of 30 millivolts, we have to reset this value and reset also the value of the recovery variable. Actually, with this model we are able to simulate many kinds of behavior of a neuron, like regular spiking, intrinsically bursting, and much other, which are different behaviors that we can observe in different neurons in our brain and in our nervous system. So this will be this is how our project will look like at the end. There's a major box subsystem in which we have the implementation of the equations of the dynamics, and then there's an additional input which is an input of current, and by tuning this input we are able to generate the different behaviors of our neuron. So without going too much in the detail, let's start. So let's start with a new open canvas, a new blank canvas. So I reported here the two equations that we are going to implement. We're going to save this. We're going to call this Neuron Video 2, for example. Okay, and then we're going to start by observing that we have to implement two ordinary differential equations. So and both of them have order 1. So we start by adding two integrators and by adding the two stubs for each integrator. Okay, so this will be V dot, this will be V, this will be U dot, and this will be U. Then we can add some constant and parameters. For instance, as you can see, we have A, B, and also, if you remember, C and D as parameters. So it is convenient, and we will see in the detail later why it is convenient to define the two constant parameter C and D with respectively C and D. So these two as a constant, while the other two parameters, it is convenient to use them as gains, so A and B, since they both appear just as multiplied by another factor. So here we have a gain with gain parameter B and another one with gain parameter C. Now, what else we need? So we need also an input current, which can be implemented, for instance, with a pulse generator. We are going to set the values, the parameters of this pulse generator later on. And then we have to implement these two equations. So first, to implement these two equations, we need a square operation. Then the result of the square operation is multiplied by 0.04, so we can add a gain with value 0.04. We can increase the size of this gain to visualize better the value of the gain. Similarly, we need a gain with value 5. Oops. Which is used to multiply V here. Then we also need a constant represented by this 140. Then we have U and I. Okay, so to implement these algebraic equations, we just need to use the block add, and then by default this block has just 2 plus, but we can modify all the list of operation by just adding plus and minus, and this will add in the block a number of inputs equal to the number of signs that we have here, with the corresponding sign in the corresponding order that we use here. So for instance, if I want to use plus 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 again, just for convenience to organize the terms, and a minus at the end, I just have to add 2 plus here and a minus, and this will be the result. So stretching a little bit, you will see that, for instance, this is useful for the plus I, this for this term, this for this term, and this for this one, and this is for U. Similarly, we can do the same stuff here. We have actually whoops, this was an A, as you can see here. So A multiplies the result of B times V minus U. So here we can add another addition block. We plug the result of B times V here. We left this empty for the minus U, but we change the operation here. And the result is multiplied by A. Then the two results coming up from the right hand side of these equations, so this corresponding to this right hand side and this corresponding to this right hand side, must be linked in a feedback loop to the U dot and V dot values. So essentially we have to do this kind of connections for V and this kind of connection for U, but to do this in a cleaner manner, we can do like this. We can use the pair of blocks go to and from. We can call this go to, for instance, with the tag F, since in the equations here we decided to call this right hand side as a function F of something. And similarly, we can do the same thing here. calling this h for obvious reason, for the same reason. And then this result can be plugged and linked to v dot and u dot, so as input for the integrators, using the other block from, and by referring inside the block from to the corresponding tag. So for instance here to f and here to h. So we are almost there. We miss something to implement the reset. So actually what we have done so far implements these two equations without any reset. We have to implement the reset and set some parameters. So an easy way to implement the reset function, that if you remember is this kind of Boolean operation with this if else statement. We can easily implement this with a MATLAB function, and by implementing that if then else inside this generated function. Observe that such a function, for instance, takes as input v, u, which are the two variables that we want to update. So this of course will be also the result of our function. Observe that when I change the number of inputs and their values and the number of outputs and their values, at the same time also the function updates itself, changing the values, changing the shape of the block, showing the added outputs and the added inputs with the corresponding names. Okay, so to implement correctly this reset function, we also need to take as input c and d, which are the two parameters that are used for the reset. And also it is convenient, we will see later on why, to provide as output also an output signals R, which can be used to understand when we have done a reset or not. This in particular is really helpful to understand when we want to give a reset also to integrator, since this can have problems in handling the discontinuities that came up in this model when we do the resets. So we can just replicate the statement that we have seen in the slides. So if v is greater or equal than 30, we have to do something, otherwise we have to do something else, actually nothing. Or better, if v is greater or equal than 30, we have to reset the value of v with c and the value of u with c plus d instead, and the value of the reset is plugged to 1, otherwise the value of the reset is 0. So this is the function that we need. We can move back to our Simulink model, and this, as you can see, is the result of the block. We have 4 inputs, 3 outputs, and named correspondingly to the order that we have used inside the function. So v is connected here, here c, here whoops, no, not exactly, but we can do like this. For convenience, we can use cd and here u, and you will see that this is nice because now all the wires are well organized. Okay, let's do like this. Perfect. So these are the connection before the reset function. Then at the end we know that v should be connected here, should be connected here, and should be connected also here, multiplied by b. Similarly, u should be brought here and subtract to achieve this term here, and similarly should be brought here to be subtract in this term here. For the values of the reset, the value of the reset, as I told you, can be used to set the reset of the integrator. This is really helpful because in these kind of models where there are some discontinuities introduced by rapid changes of the variable, for instance for rapid changes forced during the evolution of the differential equation, this can be useful to help the integrator to forget the memory of the previous samples and help the solver in the correct resolution of the differential equation. So in this case we can use the reset value in the integrator by setting that this integrator has an external reset with a rising edge. Then here we can also add an initial condition, which is actually C, since every time we do the reset we use C. And for this integrator actually we can also limit the output, since we know from biology that the maximum action potential that we can achieve is 30 millivolt. Instead, for this integrator we just add the possibility of having an external reset, again with a rising edge, and we also set the initial condition to D or C plus D. So the value of the reset is then brought in feedback here and here. But again, if you want to do something cleaner, you can also use again the couple of blocks go to and from to bring the reset signal to the two integrators. So we're almost there. We have to set the parameters A, B, C, D, and also a parameter for the input currents. So for the input currents we will set the amplitude as varying with a parameter I, which is the maximum, the peak current that we can bring to the neuron. We will fix this period of the signal as, I call this as variable stop divided by 2. This is because stop will be also the name of the parameter that I will use to set the stop time of the simulation in seconds. So similarly here I will add in the stop time the parameter stop. Then coming back to the pulse generator, the pulse width, we want this to be the 50% of the period, so actually the duty cycle is 1/2, and a phase delay of 40 seconds, just to not start with a value of I, but starting with a low value and then increasing, introducing a pulse, then moving down again, and then moving up. Now we have to set the parameters stop. So we said that we have a certain number of parameters. We have A, B, C, D, I, and also stop. We can initialize all these parameters in a MATLAB script, as I did here. So I will provide to you this easy MATLAB script in which we assign a certain value for A, a certain value for B, for C, for D, for I, and also for stop. And this can be also updated by you playing a bit, following the Izikevich paper to achieve some other behaviors of the neuronal dynamics. So we run this just to be sure that all of these values are in the workspace of MATLAB, and if they are in the workspace of MATLAB, actually they will be also recognized in Simulink. And then we will try to run our model with the default settings, so without playing with the solver type, with the solver order, with tolerances and anything. But before this, we add a scope to visualize the results. So it could be interesting actually to visualize the kind of current input that we are going to provide to our model. The action potential. Actually, I want the action potential first, because it is the kind of dynamics that you will see also in test books. And maybe that's it. The recovery variable is not so used, so it's just enough like this. We can press run to solve the model. So to visualize something, we can change the layout in this way. And this will be the result. So there's something here. There may be some issue, maybe for the tolerance used, maybe. So the model is not solved really in an exact way, probably. So to be sure that the model is solved correctly, we can go to model settings. We can change this variable step maybe, or we can change the maximum step size and the minimum step size instead of having leaving Simulink to choose these values automatically. So for instance, we may desire to have a 0.01 of minimum step and a maximum step of 0.1 second, maybe. Let's try. And this will should fix everything. So this is one way. This is one behavior of the neuronal model that we have implemented. Actually, is this one, the regular spiking. So as you can see, when you have a step of current, the neuron starts to fire in a regular way. But also in the MATLAB script that I'm going to provide to you, there's also the possibility to implement, if I remember correctly, a kind of chattering behavior. And this can be done just by changing the value of t here to 2, so to select instead of these parameters these ones. And if you do like this and you run the script, if you update again, you will find a different behavior of the neuron due to the choice of the parameters. As you can see here, also the values are going to bounce up and down, maybe again because the dynamics of the neuron here is even faster, so you would probably have to adjust the tolerance even more to be able to capture this evolution and have all these spikes at the same height. So actually this was everything for this video. I hope you enjoyed this kind of implementation, this simple implementation in Simulink. And in the links in the description there's also a shared folder with all the materials, the slides, the implementation of the model of this video in Simulink, and also the small MATLAB script with the parameters that can be changed. So thank you for your attention, and if you haven't followed our YouTube channel, please follow it, and follow also my Facebook group of the University of Pisa. Thank you.